There will come a time when the last star burns out. No explosion, no final collapse, no cosmic scream, just silence. Not the silence of destruction, but the silence of exhaustion. This is not science fiction. It is the most widely supported scientific prediction for the ultimate fate of our universe. It is called the heat death, and it may already be inevitable when we look into the night sky. The universe feels eternal. Galaxies rotate in graceful spirals. Stars ignite in brilliant flashes. Black holes bend light itself. Everything appears alive with motion. But beneath that motion lies a deeper truth. The universe is not static, it is evolving, and every measurement we make reveals the same direction, forward. The key to understanding heat death is a simple but profound concept. Entropy. Entropy measures disorder. Imagine a drop of ink falling into water. At first it is structured, distinct, separate, but within seconds it dissolves into uniformity. You never see it spontaneously gather back together. That direction, from order to disorder, is irreversible. This is the second law of thermodynamics. In a closed system, entropy always increases, and as far as we know, the universe is the ultimate closed system. In the late 19th century, Austrian physicist Ludwig Boltzmann tried to explain why entropy increases. At the time, many scientists resisted the idea that matter was made of atoms. Boltzmann argued that entropy was statistical. Order is rare because there are fewer ways for particles to be arranged neatly than chaotically. His ideas were controversial. He faced harsh criticism throughout his life, struggling with depression and professional isolation. Boltzmann died in 1906 before atoms were fully accepted. Today, his equation defining entropy is carved into his tombstone, and it quietly predicts the aging of the cosmos. Entropy alone does not doom the universe. Expansion does. In 1929, astronomers discovered that galaxies are moving away from us. The universe is expanding. But in the late 20th century, something even more shocking was discovered. The expansion is accelerating. Something, we call it dark energy, is pushing space apart faster and faster. If this continues, distant galaxies will eventually move beyond our observable horizon. One day, observers in our galaxy will see only darkness, not because stars are gone, but because space itself has stretched too far. Heat death is not tomorrow. It unfolds across unimaginable timescales. Within about 100 trillion years, star formation will end. Galaxies will exhaust their hydrogen. Only long-living red dwarfs will remain, faint embers burning slowly. After that, the last stars will die. The universe will enter the degenerate era. White dwarfs, neutron stars, black holes. No new light will appear. Much later, even stellar remnants may slowly decay. Matter itself might eventually disintegrate. And then comes the black hole era. For decades, black holes were thought to be eternal. But in 1974, Stephen Hawking changed that by combining quantum mechanics and general relativity. He predicted that black holes emit radiation, slowly, almost imperceptibly, over unimaginably long periods. They evaporate. Supermassive black holes may take 100 billion trillion years to disappear, but even they are temporary. Hawking's insight ensures that nothing in the universe lasts forever, not even darkness. After the last black hole fades, the universe enters its final state. No stars, no planets, no structure, only sparse particles drifting in near-perfect uniformity. This is heat death, not heat as in fire, but heat as in equilibrium, energy evenly distributed, no gradients, and without energy differences. Nothing can happen, no chemistry, no life, no thought. Time will continue, but change will end. The concept of a thermodynamic death of the universe was first articulated in the 1850s by Lord Kelvin. He realized that if energy always degrades into less usable forms, the universe must eventually reach a state where no work is possible. He called it the heat death. At the time, the universe was still thought to be eternal and unchanging. Kelvin's conclusion was radical. He introduced the idea that even the cosmos has a lifespan. Heat death is not the only proposed ending. Some theories suggest a big crunch, where expansion reverses and the universe collapses inward. Others predict a big rip, where dark energy grows so strong that galaxies, stars, planets, and even atoms are torn apart. But current observations suggest expansion will continue, steadily, endlessly, leading not to violence, but to silence. The end of the universe will not be dramatic, it will not be loud, it will be slow, cold, gradual, everything that ever existed, every civilization, every memory, every star, dissolving into equilibrium. And yet, we live now in a brief luminous era, where stars still shine, where energy still flows, where complexity is possible, entropy is rising, the universe is aging. But in this fleeting moment, it became conscious, and for a short time in cosmic history, the universe looked back at itself and wondered how it would end.